What if everything you see around you, the stars above, the earth beneath your feet, and even time itself, had a beginning? Over 13 billion years ago, the universe was not filled with galaxies or light. It was something far stranger, something beyond imagination. From a single moment of creation emerged space, time, matter, and the laws that govern reality. This is not just a story of stars and planets. This is the story of existence itself. In this journey, we will trace the life cycle of the universe, from its birth in the Big Bang, through the formation of galaxies and life, to the mysterious future that awaits everything we know. Let us begin, at the very first moment. Chapter 1: The Singularity. Birth of Space and Time. At the very beginning of everything we know, there was nothing familiar. No stars. No planets. No space. No time. The story of the universe begins at a moment scientists call the singularity. A point so small, so dense, and so hot that the laws of physics themselves cease to function. This is the starting point of the Big Bang and the foundation of the universe's entire life cycle. The singularity was not just empty darkness. It was the opposite. All matter, all energy, and all the building blocks of reality were compressed into an unimaginably tiny point. There was no distance, no direction, and no duration. Space and time had not yet come into existence. The universe was not born inside space. Space itself was born at that moment. This idea is difficult to imagine because every human experience depends on space and time. Yet, according to modern physics, time itself began with the Big Bang. Asking what happened before it is like asking what lies north of the North Pole. The question simply has no meaning. At the singularity, the universe existed in a state of infinite density and infinite temperature. These words do not mean extremely large. They mean that our mathematical models break down. Einstein's theory of gravity predicts such a condition, but it cannot explain what happens inside it. Quantum mechanics, which governs the smallest particles, also fails to describe gravity at this extreme. This conflict represents one of the greatest unsolved problems in science. At this earliest moment, the universe was perfectly unified. The four fundamental forces we observe today, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were not separate. They existed as a single, unified force. Matter and energy were indistinguishable. The universe was pure potential. As the universe began to expand, it also began to cool. This cooling allowed energy to slowly transform into particles. But at the singularity itself, there were no particles, no atoms, no radiation, only a unified, incomprehensible state of existence. One of the most fascinating aspects of the singularity is that it contained everything that would ever exist. Every galaxy, every star, every planet, and every living being was encoded within this tiny origin point. The hydrogen in the sun, the carbon in our bodies, and the iron in Earth's core all trace their origins back to this single moment. Although we cannot observe the singularity directly, we can see its fingerprints across the universe. The expansion of galaxies, the cosmic microwave background radiation, and the distribution of light elements all point to an extremely hot and dense beginning. These observations form the strongest evidence supporting the Big Bang theory. Yet, the cause of the singularity remains unknown. Some theories suggest quantum fluctuations in a vacuum. Others propose that our universe is part of a cycle, expanding, collapsing, and reborn again. Some ideas even involve higher dimensions beyond our perception. For now, these remain theories, waiting for evidence. What we do know is that the singularity represents the moment when possibility became reality. It is the bridge between nothing and everything. It marks the transition from absolute simplicity to infinite complexity. As the universe emerged from this state, it did not settle quietly. Instead, it entered a dramatic phase of rapid expansion, one that reshaped the cosmos in less than a second. This phase, known as cosmic inflation, would determine the structure of the universe for billions of years to come. The singularity is not just the beginning of the universe. It is the origin of all physical laws, all cosmic structures, and all existence itself. To understand it is to stand at the edge of knowledge, where science meets mystery. And from this moment of absolute beginning, the universe began its journey. In the next chapter, we explore inflation, the moment the universe expanded faster than the speed of light, shaping everything we see today. Chapter 2. Inflation. The universe expands at unimaginable speed. As the universe emerged from the singularity, it did not grow gently. Instead, it entered one of the most dramatic phases in its entire history, a phase known as cosmic inflation. In a fraction of a second after the Big Bang, the universe expanded faster than the speed of light. This does not violate the laws of physics, because it was not matter moving through space faster than light. It was space itself expanding, stretching distances at an extraordinary rate. In less than a heartbeat, the universe grew from smaller than an atom to larger than an entire galaxy. Inflation began almost immediately after the birth of space and time. At this stage, the universe was still incredibly hot and filled with immense energy. Scientists believe this energy was stored in a special field, often called the inflaton field. When this field dominated the universe, it caused space to expand exponentially, smoothing and flattening the cosmos. Before inflation, the universe may have been chaotic and uneven, but inflation acted like a cosmic reset. As space expanded rapidly, any irregularities were stretched out, making the universe remarkably uniform in all directions. This explains why the universe looks almost the same no matter where we look, a mystery that puzzled scientists before inflation theory was proposed. One of the greatest achievements of inflation theory is its explanation of the universe's flatness. Observations show that the geometry of space is nearly flat, meaning parallel lines remain parallel over vast distances. Without inflation, such perfect balance would be extremely unlikely. Inflation stretched space so dramatically that any original curvature became almost undetectable. Yet inflation did not create a perfectly smooth universe. Tiny quantum fluctuations, random variations at the smallest scales, were also stretched during this phase. These microscopic ripples in energy density became frozen into space itself. Billions of years later, these same ripples would grow under gravity to form galaxies, stars, and clusters of matter. In this way, inflation planted the seeds of cosmic structure. Every galaxy, including our own Milky Way, began as a nearly invisible fluctuation during this earliest moment. Without inflation, matter would not have been distributed in a way that allowed stars and planets to form. Inflation was brief but powerful. It likely lasted for only a tiny fraction of a second, yet it reshaped the entire universe. When inflation ended, its energy was released in a process called reheating. During reheating, the universe filled with particles and radiation, marking the transition from inflation to the more familiar hot Big Bang phase. As inflation stopped, expansion continued, but at a slower, more stable rate. The universe was now enormous, hot, and filled with energy ready to form particles. Space had structure. Time had direction. The universe was prepared for the next stage of its evolution. Evidence for inflation comes from precise measurements of the cosmic microwave background radiation. Tiny temperature variations in this ancient light matched the patterns predicted by inflation theory. These patterns are like a fossil record of the universe's earliest moments, preserved across billions of years. Inflation also explains why distant regions of the universe appear connected, even though light could not have traveled between them under normal expansion. Before inflation, these regions were close together. Inflation then rapidly separated them, locking in their shared properties. Despite its success, inflation still raises deep questions. What exactly caused it? Why did it start? And why did it end? Scientists continue to test inflation models using advanced telescopes and experiments. Each discovery brings us closer to understanding the true nature of the universe's birth. What is certain is that inflation transformed a tiny, newborn universe into a vast cosmic canvas. It shaped the large-scale structure of space and determined how matter would gather over time. It turned chaos into order and possibility into structure. As inflation came to an end, the universe entered a new phase, one where energy began to transform into particles, and the fundamental forces started to separate. This marked the beginning of matter as we know it. In the next chapter, we will explore how fundamental particles and forces emerged from this hot, expanding universe, and how they laid the foundation for everything that exists today. The universe had expanded. Now, it was ready to take form. Chapter 3. Fundamental Forces and Particle Formation. As inflation ended, the universe entered a new and transformative stage. Space was vast, energy was immense, and temperatures were unimaginably high. Yet the universe was no longer a featureless expanse. It was now ready to take its first true form, through the creation of fundamental forces and particles. In the earliest moments after inflation, the universe was dominated by pure energy. Matter, as we recognize it today, did not yet exist. But as the universe expanded further, it began to cool. This cooling allowed energy to convert into particles, following the principle described by Einstein's equation, E equals mc squared. Energy and matter were two expressions of the same reality. At first, all forces of nature were unified into a single force. As the temperature dropped, this symmetry began to break. The first force to separate was gravity, setting itself apart from the others. This separation was crucial, because gravity would later shape the universe on the largest scales, pulling matter together to form stars, galaxies, and cosmic structures. Soon after, the strong nuclear force separated from the combined electroweak force. The strong force is responsible for binding quarks together, allowing protons and neutrons to exist. Without it, atomic nuclei could never form, and the universe would remain a sea of unbound particles. As cooling continued, the electroweak force split into two distinct forces: electromagnetism and the weak nuclear force. Electromagnetism governs light, electricity, and chemical interactions, while the weak force controls radioactive decay and plays a key role in nuclear reactions inside stars. With the forces now distinct, the universe entered the era of particle formation. Quarks emerged as some of the first fundamental particles. They combined in groups of 3 to form protons and neutrons, the building blocks of atomic nuclei. Alongside them appeared electrons, neutrinos, and other elementary particles. During this phase, matter and antimatter were created in nearly equal amounts. When matter meets antimatter, both annihilate into pure energy. In the early universe, these annihilations happened constantly. However, for reasons not yet fully understood, there was a slight imbalance. Matter existed in tiny excess over antimatter. When annihilation ended, this small surplus of matter remained. That tiny imbalance changed everything. It allowed matter to survive and eventually form galaxies, stars, planets, and life itself. Without it, the universe would be filled only with radiation, with no material structure at all. The universe at this stage was a dense, glowing plasma of particles, constantly colliding and interacting. Temperatures were so high that atoms could not exist. Protons and electrons moved freely, unable to bind together. Light was trapped, scattering endlessly among charged particles. Neutrinos, nearly massless particles, began to move freely through space, rarely interacting with other matter. Even today, relic neutrinos from this early era continue to pass through Earth, silent messengers from the universe's infancy. This period established the rules of reality. The strengths of forces, the masses of particles, and the fundamental constants of nature were set during these early moments. If any of these values were slightly different, the universe might never have developed complex structures or life. As the universe continued expanding and cooling, interactions slowed. Particles began to stabilize. Protons and neutrons survived long enough to participate in the next major transformation, the formation of atomic nuclei. The universe was still young, only seconds old, but its destiny was already taking shape. The ingredients for chemistry, stars, and galaxies were now present. The stage was set for the creation of the first elements. In the next chapter, we will explore nucleosynthesis, the process through which hydrogen, helium, and the earliest elements were forged in the fires of the young universe. From pure energy, to particles, to the building blocks of everything. The universe was learning how to exist. Chapter 4. Nucleosynthesis, creation of the first elements. As the universe continued to expand after the formation of fundamental particles, it also continued to cool. Within the first few minutes after the Big Bang, conditions changed dramatically. The universe entered a crucial phase known as nucleosynthesis, the process through which the first atomic nuclei were formed. At this time, the universe was only a few seconds to a few minutes old, yet it was already setting the chemical foundation for everything that would ever exist. Temperatures, though still extremely high, had dropped enough to allow protons and neutrons to interact in a stable way. For the first time, matter could begin assembling into something more complex. Protons and neutrons collided constantly in the dense, hot environment of the early universe. When they collided with the right energy, they fused together. The simplest nucleus to form was deuterium, made of one proton and one neutron. Once deuterium existed, it could combine further to form heavier nuclei. Through a series of rapid nuclear reactions, deuterium fused into helium. Two main forms of helium were produced, helium-3 and helium-4. Among them, helium-4 became especially abundant due to its high stability. Small traces of lithium were also created, though in much smaller quantities. This entire process lasted only about 20 minutes. After that, the universe cooled too much for nuclear fusion to continue on a large scale. Yet in this short window of time, the universe produced nearly all of the hydrogen and helium that still exist today. Roughly 75% of ordinary matter became hydrogen, while about 25% became helium. These proportions were not random. They depended on the exact conditions of the early universe, its temperature, density, and expansion rate. Remarkably, when scientists measure the abundance of hydrogen and helium in distant galaxies today, they find the same ratios predicted by Big Bang nucleosynthesis. This agreement is one of the strongest confirmations of the Big Bang theory. During nucleosynthesis, electrons still could not attach to nuclei. The universe was far too hot, and any attempt to form atoms was instantly broken apart by energetic radiation. Matter existed as a hot plasma, nuclei and electrons moving freely, bathed in light. Heavier elements such as carbon, oxygen, and iron could not form during this time. The universe expanded too quickly and cooled too fast. These elements would require the intense pressures and temperatures found later inside stars. In this way, nucleosynthesis determined not only what elements existed, but also when and where others would eventually form. Neutrinos continued to stream freely through space, carrying away energy and influencing how protons and neutrons interacted. Their behavior helped shape the final balance between hydrogen and helium. Though nearly invisible today, neutrinos played a critical role in the universe's earliest chemistry. By the end of nucleosynthesis, the universe had a simple but powerful composition. It contained vast amounts of hydrogen, significant helium, and trace lithium. These elements became the raw material for future stars and galaxies. Without this precise elemental balance, stars like the Sun could never have formed, and life as we know it would not exist. As expansion continued, the universe grew darker. Light was still trapped within the plasma, unable to travel freely. But the groundwork was complete. The universe now had mass, structure, and composition. It only needed time. Over hundreds of thousands of years, temperatures would continue to fall. Eventually, electrons would slow down enough to bind with nuclei, forming neutral atoms. When that happened, light would finally escape, leaving behind a faint glow that still fills the universe today. That ancient light is known as the cosmic microwave background, and it carries a message from the time when the universe first became transparent. In the next chapter, we will listen to that message and explore the echo of the Big Bang preserved in the cosmos. Chapter 5. The Cosmic Microwave Background. Echo of the Big Bang. For hundreds of thousands of years after nucleosynthesis, the universe remained hot, dense, and filled with light that could not travel freely. Matter existed as a glowing plasma, atomic nuclei and electrons moving independently, constantly scattering photons. The universe was bright, but it was also opaque, like a dense cosmic fog. As the universe expanded, it continued to cool. Roughly 380,000 years after the Big Bang, a critical transition occurred. Temperatures dropped low enough for electrons to slow down and attach to atomic nuclei. For the first time, neutral atoms could exist. This moment is known as recombination, even though it was actually the first combination of electrons and nuclei. When atoms formed, free electrons largely disappeared, and light no longer scattered endlessly. The universe suddenly became transparent. At that instant, photons were released to travel freely through space. That ancient light has been moving across the universe ever since. Today, we observe it as the cosmic microwave background, or CMB. A faint, uniform glow that fills the entire sky. Originally, this light was extremely hot and bright, but over billions of years, as the universe expanded, the light stretched and cooled. What was once visible radiation is now detected as microwave radiation, just a few degrees above absolute zero. The cosmic microwave background is not perfectly smooth. Tiny variations in temperature, differences of only a few millionths of a degree, are imprinted across it. These subtle patterns are incredibly important. They represent the early density fluctuations created during inflation. Where the CMB is slightly warmer, matter was slightly denser. Over time, gravity amplified these differences. Dense regions pulled in more matter, eventually forming stars, galaxies, and galaxy clusters. In this way, the CMB is a map of the universe's future, encoded in its past. Scientists first discovered the cosmic microwave background in 1965, accidentally, while testing a radio antenna. That discovery transformed cosmology. The CMB provided direct evidence that the universe had a hot, dense origin, strongly supporting the Big Bang theory. Modern satellites have mapped the CMB in extraordinary detail. These maps reveal the age of the universe, its composition, and its geometry. They show that ordinary matter makes up only a small fraction of the cosmos, while dark matter and dark energy dominate its structure and evolution. The CMB also tells us about the universe's shape. Measurements indicate that space is nearly flat, just as inflation theory predicts. It confirms that the laws of physics are the same in all directions, reinforcing the idea that the universe began in a remarkably uniform state. Beyond science, the cosmic microwave background carries deep meaning. It is the oldest light we can ever observe, a direct connection to the universe's infancy. When we detect the CMB, we are seeing the universe as it was when it was less than 1,000,000 years old. After recombination, the universe entered a long period often called the cosmic dark ages. There were no stars yet, no galaxies, and no new sources of light. The universe was filled with neutral hydrogen, slowly gathering under gravity. Over millions of years, small density variations grew stronger. Gas clouds collapsed, temperatures rose, and eventually, the first stars ignited. Light returned to the universe, not as a background glow, but as brilliant points scattered across space. The cosmic microwave background remains unchanged, quietly filling the cosmos, even as stars live and die and galaxies evolve. It is a permanent echo of the Big Bang, a reminder that the universe had a beginning. In the next chapter, we will witness the end of darkness, and explore the birth of the first stars and galaxies. Chapter 6. The Birth of Stars and Galaxies. After the universe became transparent, a long and silent era followed. There were no stars, no galaxies, and no visible light. This period, often called the Cosmic Dark Ages, lasted for millions of years. Yet beneath this darkness, the universe was slowly preparing for one of its most dramatic transformations. Gravity, though weak on small scales, began shaping the universe on vast ones. Tiny density differences, first imprinted during inflation and preserved in the cosmic microwave background, grew stronger over time. Regions with slightly more matter pulled in even more material, slowly forming massive clouds of hydrogen and helium. As these clouds collapsed under their own gravity, their centers became denser and hotter. Eventually, temperatures rose high enough to ignite nuclear fusion. Hydrogen atoms began fusing into helium, releasing enormous amounts of energy. The universe's first stars were born. These early stars were very different from those we see today. Known as population 3 stars, they were made almost entirely of hydrogen and helium. They were massive, extremely bright, and short-lived. Many burned out in just a few million years, ending their lives in powerful supernova explosions. Despite their short existence, these first stars changed the universe forever. Inside their cores, nuclear fusion created heavier elements such as carbon, oxygen, and iron. When they exploded, these elements were scattered into space, enriching the surrounding gas and making future generations of stars more complex. As more stars formed, gravity pulled them into groups. These clusters grew larger, eventually becoming galaxies. Some galaxies formed elegant spiral shapes, while others became massive ellipticals. Over time, galaxies grouped together into clusters and superclusters, connected by vast filaments of dark matter. The light from the first stars began to transform the universe once again. Their intense radiation reionized surrounding hydrogen gas in a process known as cosmic reionization. This marked the end of the Dark Ages and allowed light to travel freely across vast distances. At the centers of many young galaxies, enormous black holes formed. These black holes grew by consuming gas and stars, becoming supermassive black holes. Though invisible themselves, their powerful influence shaped galaxy evolution, regulating star formation and galactic structure. Within galaxies, stars were born in nebulae, vast clouds of gas and dust. Over billions of years, stars formed and died, enriching the universe with heavier elements. Planets began forming around stable stars, including rocky worlds and gas giants. Our own galaxy, the Milky Way, formed during this era. Within it, later generations of stars provided the elements needed for planets, and eventually, life. Every atom heavier than hydrogen in our bodies was forged in the heart of a star. The universe was no longer dark or simple. It had become structured, luminous, and dynamic. Galaxies rotated, stars pulsed with energy, and cosmic evolution accelerated. Yet, much of the universe's mass remained unseen. Invisible matter continued to guide the formation of galaxies and clusters. This mysterious component, dark matter, played a crucial role in shaping the cosmos. In the next chapter, we will explore how the universe organized itself on the largest scales, and uncover the hidden framework known as the structure of the modern universe. Chapter 7. The structure of the modern universe. As stars and galaxies continued to form, the universe began to reveal a remarkable level of organization. What first appeared to be a random scattering of galaxies slowly revealed an underlying pattern. A vast cosmic design shaped by gravity over billions of years. This is the structure of the modern universe. On the largest scales, galaxies are not distributed evenly. Instead, they form an enormous cosmic web. This web is made up of long filaments of galaxies and dark matter, intersecting at dense nodes called galaxy clusters. Between these filaments lie immense voids, regions of space containing very little matter. This structure began with tiny density fluctuations present in the early universe. Over time, gravity amplified these differences. Dark matter, which does not emit or absorb light, played a critical role. It formed invisible scaffolding, pulling ordinary matter along with it. Without dark matter, galaxies would not have formed in the way we observe today. Galaxy clusters are among the largest gravitationally bound objects in the universe. They contain hundreds or even thousands of galaxies, along with vast amounts of hot gas and dark matter. The gravity within these clusters is so strong that it can bend light itself, creating effects known as gravitational lensing. Within clusters, galaxies interact and evolve. Some collide and merge, forming larger galaxies. Others are stripped of gas, shutting down star formation. Over billions of years, these interactions shape the appearance and behavior of galaxies. Beyond clusters lie superclusters, immense groupings of galaxy clusters connected by filaments. These structures span hundreds of millions of light years. Together, filaments, clusters, and voids form the largest known patterns in the universe. Despite this complexity, the universe follows a simple rule. On very large scales, it is statistically uniform. This means that while local regions vary greatly, the universe looks essentially the same in every direction when viewed over immense distances. This principle, called the cosmological principle, is a cornerstone of modern cosmology. As galaxies evolved, star formation rates changed. In the early universe, stars formed rapidly. Over time, gas supplies diminished, and star formation slowed. Many galaxies became quieter, filled with older stars. Others continued forming stars, shaped by their environments and interactions. The expansion of the universe continued throughout this evolution. Galaxies are still moving away from each other as space itself stretches. This expansion is not caused by galaxies traveling through space, but by space expanding between them. The farther a galaxy is, the faster it appears to recede. Observations show that this expansion is not slowing down, it is accelerating. This discovery revealed the presence of a mysterious force called dark energy, which counteracts gravity on cosmic scales and drives the universe's accelerated expansion. The modern universe is thus a balance between opposing forces. Gravity pulls matter together, forming structure. Dark energy pushes space apart, shaping the universe's long-term fate. Together, they govern the evolution of the cosmos. Within this vast structure, our place is remarkably small. Earth orbits an ordinary star in a spiral galaxy among billions of others. Yet by studying the universe's structure, we uncover the same physical laws operating everywhere. In the next chapter, we will dive deeper into the unseen forces shaping the cosmos, and explore dark matter and dark energy, the mysterious components that dominate the universe. Chapter 8: Dark Matter and Dark Energy, the Invisible Universe. When scientists began studying the motion of galaxies, they noticed something strange. Galaxies were rotating too fast. According to the visible matter they contained, they should have flown apart. Yet they remained intact, held together by an unseen force. This mystery led to the discovery of dark matter. Dark matter does not emit light, reflect light, or absorb light. It cannot be seen directly. Yet its gravitational influence is undeniable. It makes up about 27% of the universe's total content, far outweighing ordinary matter, which accounts for only a small fraction. Dark matter acts as a cosmic glue. It forms massive halos around galaxies, providing the gravitational framework needed for stars and gas to remain bound. In galaxy clusters, dark matter's presence is revealed through gravitational lensing, where light from distant galaxies is bent as it passes through invisible mass. Without dark matter, the universe would look very different. Galaxies would not have formed as quickly or as stably. Large-scale structures like filaments and clusters would never have emerged in their observed form. Dark matter shaped the universe long before the first stars ignited. Despite its importance, the true nature of dark matter remains unknown. It does not interact with electromagnetism, making it invisible to telescopes. Scientists propose that it may be made of exotic particles that rarely interact with ordinary matter. Experiments deep underground and in space continue to search for it. As mysterious as dark matter is, it is not the strangest component of the universe. That title belongs to dark energy. In the late 20th century, astronomers discovered that the expansion of the universe is accelerating. Galaxies are not just moving apart, they're doing so faster over time. This observation revealed the presence of a force that counteracts gravity on the largest scales. Dark energy makes up about 68% of the universe. Unlike dark matter, it does not pull matter together. Instead, it pushes space apart. Its effect grows stronger as the universe expands, dominating cosmic evolution in the present era. One way to understand dark energy is to imagine space itself possessing energy. As space expands, more of this energy comes into existence, driving further expansion. Though this idea fits observations, its true origin remains one of the greatest mysteries in physics. Dark matter and dark energy work in opposition. Dark matter builds structure, drawing matter together. Dark energy stretches space, pulling structures apart. The universe's history and future are shaped by the balance between these two invisible forces. Right now, dark energy is winning. Its influence is causing galaxies to drift farther apart, isolating them over time. In the distant future, galaxies beyond our local group may disappear from view entirely. Yet even in its mystery, dark energy provides insight into the universe's fate. It suggests a future where expansion continues indefinitely, shaping the final chapter of cosmic history. In the next and final chapter, we will look forward and explore the possible endings of the universe, from eternal expansion to ultimate collapse. Chapter 9. The Future of the Universe. Possible Endings. The universe has been expanding since the moment it was born. For billions of years, galaxies have drifted apart, stars have lived and died, and cosmic structures have evolved. Yet every story has an ending. The final chapter of the universe's life cycle lies not in its past, but in its future. To understand how the universe may end, scientists study how it expands today. Observations show that this expansion is accelerating, driven by dark energy. From this discovery arise several possible futures, each shaped by the balance between gravity and expansion. One possibility is known as the Big Freeze, sometimes called the heat death of the universe. In this scenario, expansion continues forever. Galaxies drift farther apart, stars slowly burn out, and star formation eventually stops. The universe grows colder and darker as energy becomes evenly spread. Over trillions of years, even the longest-lived stars fade away. Black holes slowly evaporate through a process called Hawking radiation. What remains is a vast, silent universe filled with cold particles and fading light. A universe that continues to exist, but where change is nearly impossible. Another possible ending is the Big Crunch. In this scenario, dark energy weakens or reverses, allowing gravity to regain dominance. Expansion slows, stops, and then reverses. Galaxies move closer together, temperatures rise, and the universe collapses back into a dense state. If the Big Crunch occurs, the universe could end much like it began, compressed, hot, and intense. Some theories suggest this collapse might trigger another Big Bang, leading to a cyclic universe that is born, dies, and is reborn again. A more dramatic possibility is the Big Rip. If dark energy grows stronger over time, it could eventually overcome all other forces. First, galaxy clusters would be torn apart. Then galaxies. Then stars and planets. Eventually, even atoms would be ripped apart as space itself expands too rapidly to hold anything together. In the Big Rip scenario, the universe ends not in silence or collapse, but in total destruction, where the very fabric of reality is torn apart. There are also more subtle possibilities. The universe may settle into a stable state, or experience quantum events that reshape its destiny in unexpected ways. The true ending remains unknown, hidden within the nature of dark energy itself. What makes these possibilities extraordinary is that they are not just theories about distant space. They are predictions about everything, all matter, all energy, all time. The universe's fate is the ultimate question of cosmology. Yet regardless of how the universe ends, its journey is already remarkable. From a singularity smaller than an atom, it grew into a cosmos filled with billions of galaxies. From pure energy, it formed matter. From matter, stars. From stars, planets. And from planets, beings capable of wondering how it all began. We are not separate from this story. Every atom in our bodies was forged in the heart of a star. Every law that governs the universe governs us as well. In studying the cosmos, the universe is, in a sense, studying itself. The life cycle of the Big Bang is not just a scientific timeline. It is a reminder that even the vast universe had a beginning, and will have an end. Between those moments lies everything that ever was, ever is, and ever will be. From the birth of time, to the edge of eternity, this is the story of the universe.